Problem 2 is called Sorta Interesting, right? Because these are some interesting, more conceptual questions we can talk about when it comes to sorting. The first thing, what does it mean to sort in place and why would we want this? Take a moment and think about that. And so in place means that we're not using significant extra space. The definition of that actually can be a little arbitrary, but in general, if it's not linear amount of additional space, then we call it in place, right? And so if let's say we were sorting an array with like 1,000 elements, if the process of our sorting algorithm meant we had to make a whole nother copy of the array with 1,000 elements, or like there's a whole nother data structure, right? Well, that is an amount of extra space linear to the number of items in the original array, which means it takes linear space, and we don't consider that in place. In general, we're going to consider something in place if it requires, definitely if it only requires a constant or very small amount of space, regardless of the input size. And some people also say that if it takes log n extra space, we can also call it in place. It's a little bit debatable, but just things that don't use like a ton of extra storage. And why would we want this? Well, computers are limited, right? They are like real physical things with only some limited amount of memory or RAM. And so we don't want to overwhelm our computer by storing like huge bunches of stuff, right? Like junk. Our computer only has so much room to store the things we want. And so we don't want to use extra space when it's unnecessary. And so just like our answers to this could just be no significant extra space and good for computer. Happy computer. That's my computer making a happy face because I'm not pushing it to the limit, right? So the next question is, what does it mean for a sort to be stable? And what sorting algorithms have we seen that are stable? Again, I'd love for you to take a moment and really think about this one because it's an interesting question. And so stable means that if you had items that are equal according to your sort, they are in the same relative order in the final result as they are in the original unsorted array. And so if we sort of want to see this through an example, let's say you have 3 dogs, right? You have dog with the name Cutie and the age 1. Let's say you have another dog that is named Woof, because you did a great job naming your dogs, right? And this dog is 3. And then let's say you have another dog named Socks. That is my real dog's name. I was 12. Don't ask me why. And so you have these 3 dogs, right? And you want to sort them according to their age. So the age is the metric by which you're comparing them. But at the end of the day, you can see that they're all different, right? And so in a stable sort, even though Cutie and Socks are equivalent according to our sort, right? They're equal in order because they are the same age 1. In a stable sort, Cutie always comes before Socks because in our original list, Cutie came before Socks. In an unstable sort, it is possible that the final result has Socks before Cutie because unstable sorts don't necessarily preserve the order. And so the result, if you're stable, is always going to be Cutie, Socks, Woof, right? Because we're still sorting by age. So the things that are age 1 go first, and then this dog that's 3 years old goes last. Whereas an unstable sort could maybe happen to give us that, but it also could do this, right? And so Socks and Cutie are not in the same places relative to each other as they were in the original array. That is problem 2. The next question asks, which algorithm would run fastest on an already sorted list? This is definitely an interesting question. So let's take a moment and pause the video. And so insertion sort is going to run the fastest on an already sorted list because there are no inversions. Let's take a moment and think about if we had an already sorted list. Well, we recall the way insertion sort works is that we start at the bottom and we move from left to right at every step, comparing just to the element before us to see if we need to swap, right? And so we start here and we say, okay, 2, do you need to swap with 1? Nope, just move on, right? We don't waste any more time there. We go 3, do you need to swap with 2? Nope. Then there's no need and we move on. When we see 4 doesn't need to swap with 3, we just instantly move on to 5. And so at every single element, all we did was one comparison with the element before it, and then we moved on. And so we get to the whole array or the list in linear time. And so that is super cool. And this is sort of a common question that you'll get asked at points. But insertion sort runs the fast on sorted lists or almost sorted lists, right? If there's only like maybe 1 or 2 elements that are out of order, you're still pretty much always moving on very quickly. And so you get this awesome linear or close to linear runtime. And so that is problem 3. Next, given any list, what is the ideal pivot for quicksort? Again, you'll take a moment and think about this. And so in our runtime analysis for quicksort, recall we said that the best case was when you can split the list in half every time, right? Because if you can split the list in half every time, then you'll reach your base case where you have single item lists in log n layers, right? And the worst case would be that you actually only decrease the array by a -1 factor every time, which means it takes n layers. And we saw this in our runtime analysis. And so if we want to split our array in half every time, then we should pick the median. And if you recall our little, I don't know, when did we learn this? Like high school, middle school, math, whatever. The median is the element that will be in the middle if your list was to be sorted. And so the median is going to perfectly rest between half and half of your lists. So we always want to pick the median when doing quicksort. The last question is, so far in class, we've mostly applied our sorts to lists of numbers. In practice, how would we typically make sure that our sorts can be applied to other types and not just numbers? So let's take a moment and think about this one. And you kind of maybe recall that earlier in the class, we were talking about this interfaces, and we were talking about the comparable interface. I guess maybe this is pronounced comparable, but I say comparable, so we're going to go with that. And so the comparable interface just requires that you implement this compare to method. And so now, given this, if we have any 2 elements that if your object implements the comparable interface, you can compare it to other things from your type. And this compare to method is going to let you know if, A is less than B according to however you define it, or A is equal to B, or A is maybe greater than B. And that is up to you to define, right? And this is really awesome because let's say, again, you define these dogs, right? And so maybe you, as the creator of the dog class, decide, oh, if I compare dogs, I want my compare to compare their ages, right? But maybe also later on you go, okay, I changed my mind. I want dogs to be compared alphabetically by their name. That's a change that is up to you. You make that design choice, but it's easy for you to just, all you have to do is change your compare to method, and your interface makes this like very clean for other people using your dogs and sorting the actual dogs. It's just contained very neatly within this compare to method. I want to note that this is only relevant for comparison sorts, right? We haven't actually learned about this yet this week, but next week you'll be covering radix sorts or like counting sorts. And so for those, you're not actually comparing any 2 individual elements, so this is not relevant there. But for comparison sorts like the ones we've seen today, having your object implement the comparable interface, and then defining that compare to method by whatever metric you think is appropriate is how we can actually make this work. And that is all of problem 2.